Okay, everyone, welcome back. We're going to talk about Chapter 2 in Chem 201, which is acid and base chemistry for organic chemists. This actually is a topic that probably has been covered if you took a Chem 101 or a Chem 110 class as your prerequisite course. Unfortunately, if you took Chem 121 as your prereq, we actually don't cover acids and bases very much until you get to the second semester, which is Gen Chem 2. So let's start. I'm going to share my screen and get rid of me. All right. So chapter 2 is looking at acids and bases, and specifically organic acids and bases. So we're going to start with some basic acid-base theory. There is an Arrhenius theory, which defines acid as a substance that dissolves in water to produce hydronium ions, which are H3O plus ions. That's an acid. A base is a substance that dissolves in water to produce hydroxide ions. That's a base. This is a slight modification of the original Arrhenius definition, which was that an acid produces H plus ions in aqueous solution. As soon as H plus is produced, it actually reacts with water because I'm in water. And what it forms is H3O plus, which is this hydronium ion. So this is a more accurate definition. HCl, when it dissolves in water, reacts with water to give a hydronium ion. This is what I was talking about before. As soon as H plus is produced, it'll react with H2O to form this hydronium ion. Now here's the reaction of HCl with water. Notice I'm going to use my curved arrows to show the change in position of electron pairs. Now you've seen these curved arrows when you did resonance back in chapter 1. We're going to use these curved arrows many, many times in this class because what we're showing here is how the electron pair, that lone pair in water, actually reacts with HCl. And this lone pair is showing me the movement of electrons. So what I end up with is this H3O, which when I calculate the formal charge, I have 1, 2, half the bonding, 3, 4, 5. It's supposed to be 6, has a positive charge on it. And then I get the chloride ion here. So this electron pair on oxygen forms this new OH bond, which is right here. This bond is broken, and those electrons end up on the chlorine here. So this is sort of what we're going to start thinking of in terms of mechanisms, which is showing exactly where my electrons are going in a reaction by using these curved arrows. Now, when I have bases, the situation is a little bit different. Many bases are metal hydroxides, specifically group 2A and group 1A metal hydroxides. These compounds are actually ionic solids, and when they dissolve in water, their ions actually dissociate. So when sodium hydroxide is dissolved in water, I end up with the sodium ion and the hydroxide ion. Any base that is not a metal hydroxide needs to be able to produce OH minus by reacting with water molecules. What we notice here is when I have ammonia, I will react with the water, and what I end up with is my ammonium ion and my hydroxide. Because this hydroxide is produced in water, it's also considered an Arrhenius base. We're going to use curved arrows to show this as well. This lone pair is going to actually attack the hydrogen, and then this pair of electrons that forms that bond is going to go on to the oxygen. So I'm forming this bond. This is the original lone pair attached to that hydrogen. I have a negative charge here and a positive charge there. Remember, nitrogen is supposed to have 5. It only has half the bonding, which is 4, so it's positive. Oxygen is supposed to have 6. It has 2, 4, 6. Half the bonding is 7, so it's negative. I get this hydroxide ion formed when the ammonia actually reacts with the water. So this curved arrow is showing me the repositioning of the electrons. It's showing me the new bond that forms and the bond that breaks, which is what we really want to focus on from now on. There's another definition of Bronsted, or of acid and base, which is called the Bronsted-Lowry acid and base theory. Here, an acid is a proton, which is an H+ donor, and a base is a proton, which is an Ace+ acceptor. Now let's think about this. Hydrogen has got 1 electron. It has 1 proton, 1 electron. And I don't care about the neutrons because I don't care about the isotope. When I lose that 1 electron, hydrogen becomes a +1 charge, and it basically has 1 proton. So this is considered a proton when it's H+. So in the Bronsted-Lowry definition of an acid, the molecule has to be a proton donor. It gives up an H+. To be a base, it's a proton acceptor. It gains an H+. The conjugate base is the species that is formed from an acid when that acid donates the proton to the base. So I have acid conjugate base, and there's a 1 proton transfer between those 2 species. I also have base conjugate acid. The conjugate acid is that species that forms when the base accepts a proton from the acid. This is called an acid-base reaction, and it's basically a proton transfer reaction. I always form a conjugate acid-base pair. I have the acid and the conjugate base, and the base and the conjugate acid. And these are both pairs of molecules that can be interconverted by transfer of a single proton. So let's look at this in the context of HCl. Here, this hydrogen is actually going onto this water, right? So I'm losing a proton. The acid is donating that proton to the base. This is a proton acceptor. This and this are related. This is the acid and the conjugate base of the acid. So this is a conjugate acid-base pair. It only differs by 1 proton. The base has these lone pairs this actually is accepting the proton. So this new proton is now on the water molecule. Remember, that's hydronium ion H3O+. This is also a conjugate acid-base pair. My base accepts a proton, which now makes it a conjugate acid. Notice this is a reversible arrow. In the forward direction, HCl is acting as the acid and water is acting as the base. In the reverse reaction, which is going in that direction, H3O plus is acting as the acid. This is now donating the proton to the Cl minus, which is forming HCl and base. So my conjugate acid is reacting with the conjugate base. This is now a proton donor in the reverse reaction. This is a proton acceptor in the reverse reaction. So my acid in the forward direction becomes my conjugate base in the reverse direction, and my base in the forward direction becomes the acid in the reverse direction. These pairs only differ by one proton. So let's try this. Label the acid, the base, and the conjugates in the reaction below. So notice this hydrogen is actually being transferred, right? This hydrogen, this is donating the H plus, so this is the acid. This is accepting the H plus, so this is the base. This is now the conjugate acid of the base. Remember, this and this are now conjugate acid-base pair. And then this is the conjugate base of water, which is the acid. So this and this are a conjugate acid-base pair. You have to know how to identify which is an acid and which is a base, which is the conjugate acid and which is the conjugate base. And you have to be able to identify the acid conjugate base and the base conjugate acid pairs. That's a skill you need to master in order to go forward in the class. Here's another question. In the following acid-base reaction, the indicated molecule is functioning as a what? Well, let's just talk about this. Here's my nitrogen with the lone pair. Here is my nitrogen. Now it has a hydrogen attached and it has become now positively charged. So this is my base because it's accepting a hydrogen. This is the hydrogen that's being lost. So this is my acid because it's donating that H plus. It leaves the electrons behind, right? Those electrons from this bond are still here, which gives it a negative charge. So this is the conjugate acid of the base, and this is the conjugate base of the acid. So this is the conjugate acid-base pair, and this is that second conjugate acid-base pair. we're always going to use these curved arrows to show the flow of electrons that occurs in the transfer of a proton when we do this acid-base theory. So let's look at this one. Here I have acetic acid. This is the hydrogen that's being donated. Here's so this is going to be my acid. This is going to be my base because it's accepting the proton. But notice this lone pair of electrons on the nitrogen is actually attacking the hydrogen. These electrons that bond is breaking. I'm only getting the H plus transferred. These electrons here are staying on the oxygen. So this becomes the conjugate base, and this are one pair. This becomes the conjugate acid, and this are the other conjugate acid base pair. So this is the bond that's broken, resulting in that negative charge on the oxygen. This is the bond that's formed, that used to be the lone pair, to that hydrogen. The flow of electrons shows me how this proton transfer acid-base reaction actually occurs. So the making of bonds and the breaking of bonds involves electron movement. We're going to use these curved arrows to describe the flow of electron density. I always go from high electron density to low electron density. That's always my flow of electrons. These are the same curved arrows that we use to draw resonance structures, but here I'm actually describing the physical movement of reaction of electrons to make and break bonds. So this is describing a chemical reaction. Again, here's my lone pair. That's going to be an area of high electron density. This is usually partial positive, partial negative. So this is low electron density. These electrons attack the hydrogen. These electrons go on to the A to become A minus. And then this is the new bond that's formed. So this bond is broken. This bond is formed. I'm tracking my electrons in order to figure out where they start and where they end. And I'm going to go from high electron density to low electron density. So high electron density is going to be lone pairs. So this is going to be lone pairs and negative charges. Low electron density is going to be partial positive and positive charges. That wants electrons in order to balance out those partial positives. This is sort of what we describe as a mechanism. Knowing how to draw mechanisms is extremely important in organic chemistry. You have to be able to reproduce this movement of electrons on tests and quizzes to describe the making and the breaking of bonds due to this electron movement in a chemical reaction. So consider this specific acid-base example. This is a negative charge, right? This is high electron density. This is partial positive. This is partial negative. This is low electron density. The base is attacking the acid. That's represented by the arrow. That pair of electrons is attacking the acid. These electrons, so that's forming the new bond. This lone pair to this hydrogen is forming the new bond. this bond is breaking and those electrons end up on the oxygen, forming a negative charge. So what I get is water. This is going to be the conjugate acid of the base because that is accepting the proton. This is donating the proton. The acid cannot lose its proton without the base taking it. All acid and base reactions occur in one step. The mechanism is showing those two arrows that indicate that two pairs of electrons move simultaneously. One shows a bond breaking, the other shows the bond that's made. These curved arrows in reactions is really, really, really important to know. Eventually, we're going to get to pushing a lot of arrows in a multi-step reaction mechanism. So for example, this lone pair is going to act as a base, and this actually is H3O plus hydronium ion. That bond is breaking. Look at the change. This oxygen becomes protonated with that hydrogen, becomes positive charged, right? That's one step. That's a proton transfer reaction. Now, what if this group actually decides to leave? This is the loss of a leaving group. Water is a neutral molecule. So sometimes if it forms something that's stable, this is a carbocation where I have a positive charge on the carbon because these electrons actually left. Now, this can also act as a base and get this hydrogen, which then makes that bond. I form this new carbon-carbon double bond, and I'll form H3O plus in that as well. This may seem really, really complicated, and it is. I'm just showing you that this is our ultimate goal. Later on, we're going to look at mechanisms that describe all these steps. This is a proton transfer step, and this is a proton transfer step, because all that changes is one hydrogen in between. So we'll get to that point in the future. This is a chart of various Bronsted-Lowry acids and bases. In this column, I have the acids and then the name of those acids. This is the conjugate base. This is when I've lost an H plus. Notice HI becomes I minus. That's the difference in one hydrogen plus. We're going to look at acid and base strengths next. As I go up this chart, my acid strength is increasing. Notice the conjugate base increases in the opposite direction. We're going to talk about that a little bit later. What you really want to look at here is note the acid, I lose a hydrogen, I become the conjugate base. H2SO4, I lose a hydrogen, I become HSO4 minus. Right? You want to look at the transfers of these protons. You want to be able to take an acid and figure out what the conjugate base is, or take a base and figure out what the conjugate acid is. So if these are bases, these are now the conjugate acids if I go in the other direction. So you need to be able to sort of look at these proton transfer steps, recognize when I have an acid conjugate base pair, and also recognize how my electrons move when they do this proton transfer reaction. Here's a couple things I want you to note about that table. An acid can be positively charged, neutral, or negatively charged. Hydronium is a positively charged acid. It will form water when it loses an H+. Carbonic acid will form HCO3- after it loses a proton. That's a neutral acid. It loses a proton and becomes negatively charged. This has 2 protons to lose. If it loses one, it becomes HPO4 - 2. I lost one, I had 2, now I only have 1. So this is going to be the acid conjugate base pair for that. Notice also from the chart that bases can be negatively charged or neutral. So OH-, Cl-, those are examples of negatively charged bases. Ammonia is an example of something that's neutral that is going to act as a base. Acids can also be classified as monoprotic, 1 proton to transfer, diprotic, 2 protons to transfer, or triprotic, 3 protons to transfer. I'm going to do this sequentially. Like my H2CO3 is going to go to HCO3-. This is an acid conjugate base pair. This is now an acid, and when it loses a hydrogen, it becomes CO3-2-, which is the conjugate base for that. So this is a pair, and this is a pair. H2CO3 and CO3-2- are not conjugate acid-base pair because I can only have a difference of 1 proton. H3PO4, phosphoric acid, will go in 3 successive steps. It forms H2PO4-, then that's the acid, it forms HPO4-2-, then that's the acid, it forms PO4-3-. So make sure you can understand what happens when I have 1, 2, or 3 protons that can be lost in this. This is another example of what I just said. When I look at carbonic acid, I have 1 step, right? This is the acid. This is going to be the conjugate base. This is my bicarbonate ion. So this is an acid conjugate base pair. In my new reaction, so this is the first proton transfer reaction. This is my second proton transfer reaction. This is now my acid, and this is now my conjugate base. So this is another acid conjugate base pair. It loses its protons sequentially, stepwise. I can only relate each individual stepwise pair. And notice that this bicarbonate ion is both a conjugate base and an acid. That's called amphoteric, when it can act as an acid or a base. It's also called amphiprotic. Those 2 words mean I have a species that can act as an acid or as a base, depending on the circumstance. Water is also a really important amphoteric substance. I can accept a proton to become H3O+, or I could lose a proton to become OH-. If I accept a proton, I'm acting as a base. If I lose a proton, I'm acting as an acid. Now notice, several molecules and ions can act as both an acid and a base, what we were just talking about. Again, that's that amphoteric property or amphiprotic. You'll see both terms. There's also an inverse relationship between the strength of an acid and the strength of the conjugate base. The stronger the acid, the weaker the conjugate base. HI is the strongest acid in that table. I minus is the weakest base. So if I increase acid strength, I decrease base strength. And that would be conjugate base strength. Acetic acid is a stronger acid than carbonic acid, which means acetate is going to be a weaker base than bicarbonate. You'll also need to look at this. By using that chart, by knowing what is strong and what is weak, what can I say about the conjugate acid or base of that compound? So we're going to do a lot of analysis on acid and base strength. That's a topic for another day, though. Right now, we're done for the component of Chapter 2 that we need to know this week. There will be further lectures to come as we enter the next week in our course. Enjoy acids and bases. I am going to say goodbye now, and I will see you soon.